I'm still waiting, and I'm still waiting, and I'm still waiting. Anything? Is it live yet?
It's live.
It's live. Okay, here we go. Now, mute. Ha! I got it. I caught it. All right. Hi, everybody. We're here. We've got Alex. We've got Ozzy. We're going to start Logic 101. I told Alex that I thought we could get a lot farther than he thinks we can get. So I think what we'll do is just let him go and take it from there. So meanwhile, I'm going to, Alex, while you start, and go ahead and present yourself and present whatever it is that you want to present. And I'm going to try to do housekeeping stuff like invite the people and stuff like that. Okay?
Okay. Yeah, cool. So the plan was that we would go through the first, Helena wants to do the first 4 lectures in the Introduction to Logic course, which I have, which is about 12 or 13 lectures long. So we'd do the first third of it today, was the idea anyway. So what I'm going to do is just pull up 4 lecture series in slides. We'll just go through them from there. So let me grab one of them first, lecture 1. So this is the first in a possibly 3 or 4 part series in Introduction to Logic. So that's screen sharing now, presumably, yeah?
Yep, and did you push the sort of broadcast, so it looks like when I talk, my picture comes up? So you want to go over to yourself, or
yeah, present to everyone.
Yeah, present to everyone. There you go. There you go. Okay.
Okay, good. So is that full screen, or is it just?
So I see. I'm sorry. I'm not sure what you're asking.
Is it the slide inside the options and the sidebar and stuff, or is it a full screen?
It is. So what I see is I see your slide. I see someone who's like preparing their PowerPoint, right? So I see all the stuff on the left, all the different like, you know, you click on the next one, click on the next one, that kind of thing.
Yeah, right.
I think it's perfectly fine. I mean, I think, in my opinion, everybody could probably see this.
Okay, good. So we'll just crack on with this then. So this is an introduction to formal logic, and yesterday we were talking about informal fallacies. So this is going to be the nuts and bolts that we were talking about, which is underneath those patterns of reasoning, problems in the patterns of reasoning we were going through yesterday. So let's just quickly get through this. And so what is logic? What do we mean by logic? So it's what we're talking about is the study of correct reasoning. It's what we need to have to enable us to do philosophy correctly, but it's also used in all of these other things. Yeah, okay, obviously the stuff that's on this slide, really, I'm just reading that out, but what we're going to be looking at is what makes an argument correct or not. That's like the key thing that we're going to try and get out of this course in particular, and we'll go into it in loads of detail so that it's very, very clear. So, right, this is really basic, but obviously arguments consist of premises and conclusions, and what we're trying to do is argue for the conclusion based on the premises. So we're going from the premises to the conclusion. So here's some arguments. The first one, really obvious, all Greeks are mortal, Socrates is a Greek, therefore Socrates is mortal. Second one, this is something I got from Aristotle about poetry, and then there's one I made up underneath about Tony Blair and the war in Iraq. It was a few years ago when I made this, it was a bit more relevant. So let's just have a look at how these things are broken up into their propositions, the premises and the conclusion. So here, let's take this one to begin with. So these are the 3 parts to the argument. That's the first premise, that's the second premise, and that after the word therefore is the conclusion. This one's slightly more complicated, only in the sense that we split it up into its 2 sections, and you find that actually the premise has come last and the conclusion was there first. So when you say an argument in normal, ordinary language, you can't always guarantee that the first thing somebody's saying is the premise and then they're leading into the conclusion. Sometimes I'll start with the conclusion and then give the premise afterwards like that. So if we switched it around, so the premise was first, it would say poetry expresses universal in history in particular, therefore poetry is finer and more philosophical than history. Right? That's that argument turned into the standard premise conclusion form. And then here's a different argument that's got a load of unnecessary or possibly unnecessary buffer around the propositions. So let's split it up. And then I'm just going to identify the proposition in it. We don't really need to worry about the we all know that. We just think if there were no weapons of mass destruction in Iraq, then Tony Blair was a liar. That's the first premise. And equally, we can get rid of that first bit. With hindsight, we now know that. It's just the second premise is there were no weapons of mass destruction in Iraq. And then the conclusion is just Tony Blair was a liar. So that we can abstract away from some of the stuff that we get when people ordinarily talk about things and just think about the propositions that are expressed in those premises. Sometimes those extra words will be important, sometimes they won't. What we're going to be doing is looking at propositional logic, so we want to abstract away from everything other than the propositions in those premises. So sometimes conclusions come before premises, sometimes premises and conclusions are not separate sentences, like in that middle one. Sometimes the conclusions and premises are buffered with other sentences which we can ignore. Yeah, and you should be able to apply this to reading normal everyday stuff. Like on the TV, I don't know, Trump, presumably, if you're watching him talk, if he ever says something coherent enough to be an argument, I'm sure you could delete all of the irrelevant buffers around it and find some kind of core propositions that he's saying. Yeah, okay, cool, let's just carry on with this. So this is quite important to realize that what a premise is, what a proposition is really, I suppose. A proposition is something which is true or false. So propositions are expressed by declarative sentences. So a declarative sentence is a sentence which is trying to state a fact. So the sentence, Alex is a lecturer, is stating a fact. The question, is Alex a lecturer, isn't trying to state a fact, and it's not true or false, it's just a question. And equally, the request, please stop lecturing Alex, is not you wouldn't say that it was true or false. These are other types of speech acts which can be successful or unsuccessful. You know, if you say stop lecturing and I do, then you've said something that's successful. But it's not right to say that what you said was true. Unlike if you say Alex is a lecturer, then that's true or false depending on what the world is actually like, basically. So premises and conclusions are propositions which are basically expressed by declarative sentences.
So a proposition is a declarative sentence, something
That's
that
right.
could, in theory at least, be either true or false.
Right. A proposition is something that's expressed by a declarative sentence. So it's not the same as a declarative sentence, but it's what you say when you say a declarative sentence. It's the content of that sentence. And technically speaking, a proposition is what's true or false, not a sentence. The sentence is kind of a thing that points you to the proposition, but isn't actually the proposition. So let's see. So here's the difference between propositions and sentences. If propositions were sentences, then these two bottom examples would be different arguments, right? If premises were sentences, then these would be different arguments, right? Socrates is unmarried, therefore Socrates does not have a wife, and Socrates is a bachelor, therefore Socrates has no marital female partner. If premises were sentences, these would be different arguments. But it seems that they're in fact just two different ways of saying the same argument. So underneath the sentences, we've got this kind of deeper logical, the actual argument itself is of a level which is underneath the surface grammar of the sentences. Right? So both of those two are actually just different ways of saying exactly the same thing.
So sentences express a proposition, and so two different sentences can express the same proposition.
Exactly. So right. So Yeah, I've said this really. So two or more declarative sentences might express the same proposition. So here we have a picture which explains this fairly clearly, I think. So Socrates is unmarried, Socrates has no wife, and Socrates is a bachelor. Each of those is three distinct sentences, but each of which expresses the same underlying proposition, which is about Socrates having the property of not having a wife, essentially. You can state that as being unmarried, being a bachelor, or having no wife. It really means the same thing. So when we're doing logic, all we're trying to say is really, if you said an argument in English, or if you said it in French, or if you say the same argument but state it in terms that are synonymous with one another, that doesn't mean that they're different arguments. There's some kind of idealized logical structure, which is what the real actual argument is, and that's what the propositions which have truth values actually are. Now we can go into the metaphysics of what a proposition is, and it's quite contentious, but really all that needs to be kept in mind is that a sentence, with its grammar and its idiom and its in the language that it's in or whatever, all of that grammatical linguistic stuff can be put to one side, and we just need to think about the logical structure which is underneath that. So we have blitzed through that first lecture fairly quickly. So is that okay? Does that make sense?
It does make sense to me.
Wonderful. Wonderful stuff.
Okay, great. So let's just assume that everyone's cool with that, and then if not, they can always go back, and all of the slides will be on the video, so everything can be watched again if I've gone over something too quickly. So let's just. I'm going to have to stop screen sharing that for a second, and now I'm going to screen share this one. Okay, so now we should have Logic 2, Lecture 2 screen sharing, is that right?
Yep, see that.
Yeah, okay, great, cool. So, all we've done so far is just talk about arguments, arguments being premises and conclusions, premises and conclusions being propositions, and propositions are the sorts of things that are true or false, and they're the sorts of things that are expressed by declarative sentences. So, we had this picture already, same underlying proposition by different sentences. So what we're going to look at now is what validity means, and the notion of logical form, and see how, see if we can get to grips with the idea of logical form and compare it to like musical form and poetic form, whatever. Okay, so validity is a property that arguments have. Remember, we just said a minute ago that truth or falsity is a property that propositions have, premises or conclusions have. So it's wrong to call a proposition valid, and it's wrong to call an argument true. Right? Arguments are valid or invalid, and propositions and premises are true or false. So validity is basically the core concept in logic. It's what we're doing when we study logic. So an argument is valid if the truth of the premises guarantees the truth of the conclusion. That is, if there's no situation in which the premises are true and the conclusion is false. What we're doing is looking at deductive validity. So there's another type of validity, inductive validity. So an inductive argument is where the truth of the premises makes the truth of the conclusion more likely. We're not going to be looking at those types of arguments. So from here on in, validity means deductive validity, and the definition of it is here. An argument is deductively valid if the truth of the premises guarantees the truth of the conclusion, and it's not deductively valid if that's not the case. Right, exactly. An argument's invalid if the truth of the premises does not guarantee the truth of the conclusion. Okay, so let's look at this argument. God knows the future. If God knows the future, then humans have no freedom. God does know the future, therefore humans have no freedom. Right, so let's split this up into the premises and the conclusion. Here's another argument with the same structure. If Nick Clegg has good hair, then Yeovil Town will win the Champions League. Nick Clegg does have good hair, therefore Yeovil Town will win the Champions League. That's a picture of Nick Clegg, and it just seems to me that he's got terrible kind of like Lego man haircut thing that's stuck on there. So the point of this is just that the premises of an argument can be true or false, and it doesn't change the fact that the argument is valid. Right? Possibly in the first argument, you might think that the premises are true and the conclusion is true. Who knows? In the second one, because it's so obvious that Nick Clegg has shitty hair, it just means that it's still valid even if the premises are false. It just means that if the premises were true, then the conclusion would have to be true. The conclusion follows from the truth of the premises,
So
even if
just,
they're obviously false.
so just to underscore that, to say that an argument is valid is not to say that the conclusion is necessarily true. Only
That's
that
right.
it's true if the premises are true.
Exactly. Yeah, that's it.
So this is a difference between sort of validity and soundness.
Mm.
Yes, that's right.
Yeah.
So an argument is sound if it's valid and it has true premises.
Right. And so a lot of times people, I mean, I think this is relatively, it doesn't make that much difference, at least with respect to G+ and YouTube, but I think it's important. So a lot of times someone will quote unquote run an argument and and it will be valid, but people will think the premises are shit, and they will say that's not even valid.
Right, yeah.
And so we just want to be careful. Valid is about this formal stuff that we're going to learn now, and soundness is about sort of, to me at least, sort of the meaning, the actual, let's get into the specifics of each premise and talk about it. But
Yeah,
so to me at least, first you want to look, is the argument valid? Like, is the form okay? And you should do that first, because if the form's no good, then it doesn't even matter whether the premises are true or not.
That's right. So if you're, to the extent that you are rational and engaged in a genuine debate, you would have to accept the conclusion of a sound argument. That is, if the premises are true and the premises do in fact guarantee the truth of the conclusion, then you have to accept the truth of the conclusion, right? So if someone presents you with an argument that they claim is sound, you have two options to denying the conclusion, if that's what you want to do. You can either say that the premises are not true, or you can say that the argument is not valid. So you're either saying your starting point is wrong, or you're saying maybe the starting point is right, but the starting point doesn't get you to the end point. So there's two tactics that you can do when faced with an argument that you want to disagree with, and that's basically either saying that it's not sound or saying that it's not valid. If it is sound, you really should accept the conclusion.
So would you agree that it might behoove the other person to first check if it's valid before they even bother with soundness?
Yeah, I mean, so soundness is a necessary condition. Validity is a necessary condition for soundness. So if it's not valid, then it won't be sound. Soundness means both valid and true premises. So yeah, if it's not valid, then they haven't got anywhere at all. It's like the starting point you need to get to. There's no point just having true premises and an invalid argument. And there's no point just having a valid argument and false premises. You need to have both of them if you actually want to persuade the person of your conclusion. But right. So let's just to be clear, though, a valid argument just means if that was a legitimate starting point, then you have to accept the conclusion. That's all validity means. Doesn't mean it doesn't mean that it's true. Doesn't mean that it's persuasive. It doesn't mean that valid in colloquial usage means something like acceptable, okay, or I don't mind that thing, or something. It's valid to say that or something. Valid in logic means a very specific thing, which we've given quite clearly so far.
Right. So what we really want is a sound argument. To say that something is a valid argument, it logically speaking, is not to pay it a very high compliment at all. It's a kind of minimal hurdle. Oh, wow, great, a valid argument. Well, okay, now let's see if the premises are true. Really what we're looking for ultimately is soundness. That's what we're really after ultimately.
That's true if what you're trying to do is to get someone to accept the conclusion.
Right.
From the purposes of a logician, they're not in the business of telling you what's true or false. What they're in the business of doing is telling you what follows from what.
Right.
So they don't care. I mean, I don't know whether Nick Clegg has good hair or not. Right. That's not for me to say as a logician. All that I'm here to say as a logician is whether or not it follows, if anything indeed follows from the fact that he has good hair. Right. So the logician is like a lawyer who's not here to tell you whether or not you're guilty, but is to tell you whether or not you would be convicted on that evidence. Right? He doesn't care if you actually did it. He's just telling you whether that evidence would be enough to put you away. That's what the logician's job is here.
That's a good analogy. I like that.
Okay. Right. So the moral of this story so far is that arguments can be valid even if all the premises are false and the conclusion is false, because all a valid argument means is one where it can't have true premises and a false conclusion. So validity is a relationship between the premises and the conclusion. And valid arguments can have false conclusions. And if you need anything to remember, just picture Nick Clegg and his crappy hair. This probably won't mean very much to North American people, but and probably doesn't really mean anything to UK people now. He lost the election so badly. But in 2011, when I gave this, that was really funny because he was the coalition partner and in the news. It was in the heyday of Clegg mania, if anyone can remember.
Yeah, yes.
Yeah. All right, cool. So here's two invalid arguments. If it's night, then it's dark, therefore it's night. That's actually a version of the affirming the consequent fallacy that we talked about yesterday. And nobody's ever seen a black swan, therefore there are no black swans. That's a version of the inductive fallacy that we looked at yesterday. So in both of these cases, the premises could be true and the conclusion could still be false. Right? It doesn't necessitate the conclusion being true just because the premises are true. We're going to go into this in more detail, but it's just an example of false, invalid arguments. So even though they both sound or can sound like they're valid, right? The first one, if it's night, then it's dark. It is dark, therefore it's night. That everybody has a tendency to do that. It might even be like wired into our psychology or something that we hear that type of argument as being valid, even when it's not. So it's easy to be misled down this garden path. Someone could hoodwink you by giving you an argument that sounds like it's valid when it isn't. So in logic, what we need to do is to be able to have an actual method to test whether or not something's valid. It's no good just saying, well, I know all the fallacies off by heart, and I can just hear, and I'm so clever that I can always hear correctly and tell when an argument's valid or not. You actually need a mechanical technique. So this was because the reason that formal logic got started was really that there were mathematicians who were trying to prove theorems or whatever. But often what you do is you'd say, look, it's intuitive here that this thing follows from that thing. And often it would be intuitive or whatever, but what you'd need to do is have steps that were better than intuitive, that were kind of transparently obvious, and then reduce a proof, a mathematical proof, to a simple series of each step being one example of a kind of sanctified inference. And if you could show that there was nothing other than just simple steps in there, that would be a way of guaranteeing that the inference that you'd made wasn't just intuitive, but was actually logically valid. So that's where formal logic comes from. That's what we're doing now, is analyzing arguments and showing that each of the individual steps that they take in a good argument is just nothing other than a very small, transparently obvious building block. And I can remember doing this lecture at one point, and someone asked me, well, when are we going to do the interesting inferences? And I had to say to him that there aren't any interesting inferences. All there are is like lots of very little inferences built up together. So there's no such thing as like a big jump in logic. That's just it. The whole point of it is really to scale back from big jumps and make it little jumps so that we know that we never make any mistakes. Yeah. That's really the key to it. So how do we show that an argument's valid? So we need to identify the form of the argument, and then show that all arguments with that form are valid, and then conclude that the argument that we're looking at is valid because it has that form. So that's what makes an argument valid, is the form of the argument. So we're going to move from a particular argument to a general form to enable us to see that this particular argument is valid. Like that's the strategy. So this might be really painfully obvious, but form in music is like this. This piece of music has the following form: A, B, A, right? The first bit and the second bit, and then you repeat the first bit again. Here's a bit from poetry. It's A, B, A structure. Sorry, A, B, A, B structure. And then, I don't know if anyone knows this song, but that has the structure of just A, the whole way through. It's a really terrible song. So it's really intuitively obvious what the idea of form is in logic, in music, and in poetry, and it's the same idea in logic as well. So logical form, we're going to be abstracting and starting to use symbols here. So here's this argument again: God knows the future. If God knows the future, then humans have no freedom. God knows the future, therefore humans have no freedom. Right. So we've got the same proposition repeated twice. If God knows the future, and we've got this second proposition repeated twice, then humans have no freedom. So if we call God knows the future proposition P, and if we call humans have no freedom proposition Q, then we can write it out like this: if P, then Q, P, therefore Q. And because we know that, well, because that argument form, if P then Q, P therefore Q, is valid, we then know that this argument, if God knows the future, then humans have no freedom, God knows the future, therefore humans have no freedom. We know that that argument is valid because it instantiates this form, and any argument with that form is valid. So we don't care about the content of the argument. As a logician, we just care about the form of the argument. Like I said before, we're not interested in whether or not the premises are true. We don't really care what they are. All we're doing is giving advice to our client as to whether those premises lead to that conclusion. And abstracting away from an argument to its logical form is the most important thing that you can understand as taking this course or listening to this lecture. Logical form is the key to understanding logic. Not being misled by the particular argument that's in front of you and being able to think about the form of the argument is the main thing. I can't stress that too much.
Yeah, if I could interject one little thing here, like
yes,
this is what is sometimes meant when people talk about minding your P's and Q's, right? if the argument is of the form if P then Q, P therefore Q, you have to make sure that that you don't get your P's and Q's mixed up. It doesn't matter what you substitute in for P and Q. P and Q can be any proposition. As we said earlier, they don't have to be true. We're concerned with validity here. But as long as you are consistent in your substitution of P and Q throughout the argument, it doesn't matter what P and Q are. If the argument follows the correct form, then if the premises be true, then the conclusion is guaranteed. So what Alex was trying to say here is that what we do very often here when we're considering the form is we'll take natural language sentences, we will translate those into P's and Q's, make sure that they follow the correct form, and provided they follow the correct form, then we can declare whether or not the argument is valid. You can do this for any natural language sentences.
For me, one of the funnest things, having gotten the PowerPoints a little bit ahead of time, was playing with that. So at the end of the lectures, there's a little quiz, and the first several questions of the little quiz I was able to do, which is exactly translating the natural language into the I guess grammar or calculus, and going backwards and forwards. So I think that's going to be really fun. And I really want this first lecture to get into sort of how to do that and truth tables and things. So let me just ask real quick, does anybody have any questions, or so far, did anything that was said so far need to be restated or freak you out or anything like that, or are we all on board and ready to move?
Yes, very, very clear. Very, very clear.
I agree. Really, really great. All right, so let's go on. Let's push it, man.
Okay, good. So I'm just going to give you a few more argument forms. So this one, it's sunny and it's hot, therefore it's sunny. That means P and Q, therefore P. Is kind of obvious, I guess. If the coin landed heads, then Bob won his bet. It's not the case that Bob won his bet, therefore it's not the case that the coin landed heads. We can identify the propositions in the same way. So this has a form if P then Q, not Q, therefore not P. All of these are valid. I haven't told you why they're valid yet.
That's modus. Is that modus tollens or something? That one.
Yeah, that's modus tollens. That's it. Exactly. Right. Okay. Good. So really, this is all we've done. We've looked at 3 argument forms. I haven't told you how you determine whether or not they're valid. But what we've done is just seen that you can abstract away from an argument that's said in natural language to its logical form. And what we're looking at here, the if P then Q, P therefore Q, that's kind of halfway between the grammatical form and the logical form. It's much closer to the logical form anyway. So we're kind of digging deeper. And then here's Russell on logical form. Some kind of knowledge of logical forms, though with most people it's not explicit, is involved in all understanding of discourse. It is the business of philosophical logic to extract this knowledge from its concrete integuments and to render it explicit and pure. So Bertrand Russell, one of the key kind of early developers of philosophical logic, gushing about how important it is that we get to grips with the idea of logical form. Yeah, as you can tell, I'm a big fan of logical form. Yeah, okay. So that's the end of the second lecture. I'm just going to plow on, right? Screen share. Lecture 3. Oh, is that showing lecture 3? Yep, it is, isn't it? Good, good. Okay, so what we just looked at, logic is the study of arguments. Argument is a set of propositions. Logical form of an argument is obtained by letting letters stand for the various propositions so that we can see the relations that they have to one another. So here's an argument: if Chris drank tequila, then either he went crazy or he fell asleep. I heard that he did drink the tequila, but it's not the case that he fell asleep, therefore he went crazy. I think I did have a friend called Chris who drank some tequila and went crazy around the time I was writing this. So here's slightly more complicated. It just has 3 different propositions involved in the argument. And the first bit just says if P, then Q or R, P and not R, therefore Q.
So if you wouldn't mind, let's take your, oops, did I somehow, thank you. Yeah, let me just broadcast you because for some reason present to everyone. Okay, so go back 1 slide.
Uh-huh.
All right, and let's, and maybe 1 more. Okay, so now what we want to do is just abstract these, right? So if Chris drank tequila, then either he went crazy or he fell asleep. So let's start there. So let's see. We don't care about the if. That's an operation, or as you call it, a connective. So let's see. So Chris drank tequila. That, to me, seems like an important thing. Let's call that P. Right? Then either he went crazy, right? So let's call that something, going crazy, or he fell asleep. Let's call that something. So we'll call Chris drank tequila something, and we'll call going crazy something, and we'll call falling asleep something. Okay. So there it is.
Q and R. Yeah.
And that you call a dictionary, which I think is adorable. That's the legend or the dictionary, right? So when a logician says create a dictionary, they just mean make a legend. Okay. So all right. So there we go. So we've got P, Q, and R.
So what we're doing is we're identifying the propositions that have been expressed in those sentences. So there's one sentence: if Chris drank tequila, then either he went crazy or he fell asleep. And then there's 3 propositions that have been like logically related to one another in that sentence. And the form of it is if P, then Q or R. So the P, Q, and R are propositions, and then if, then, and or are examples of connectives. They're ways of gluing those propositions together. So one way of thinking about it is that the P, Q, and R are like atoms, and if P, then Q or R is like a molecule that we've made by gluing those atomic propositions together with these connectives. And so
and I loved thinking about it that way, thinking about each individual little proposition as an atom, and then thinking of the argument itself, or once you add the operations, or in other words, the connectives, right? Because it seems like logicians say connectives, not operations or operatives or anything like that. But once they are connected, you've made yourself a little molecule. I loved that.
Yeah. So think of connectives as the bonds between the molecules, right? That's the way to think about this.
Is if a connective? I'm not sure that it is it?
If then is a connective. Yeah. If then. You know,
if then is sort of the same as saying implies that.
Right.
Right. So, but let's not get ahead of ourselves because we're going to get to this really soon.
Okay, just one thing. I'd just like to say this differs quite a little bit here from the way you would code this, because that would be regarded as invalid, where you've got an if P, then Q or I can't quite read that. Right. Because in computing, what you would say, you'd say if P and something, then Q, or if P and something else, then you have an if-then-else statement. So that wouldn't be regarded as sort of valid computing. I'm just interested to see that's how that is formatted differently from a sort of in a piece of software
well, so
in a
this
language.
is really interesting because I was like, it seems at least in the first 4 or 5 lectures or so that they talk about this implied thing, and it's almost like they arbitrarily assign sort of values. So I think we'll get into that, but I agree that
in
that's
other words, in
the
computing,
most interesting thing.
you can't have a queue, or you can't have something that varies after the then. The then has to be a singular thing, and then you have to have the condition. You have to have multiple conditions with a single then afterwards. So that would be quite a bit naughty in the as a definition of computing language.
Right, so he'll talk about this very thing.
Oh,
yeah,
right. Oh, okay.
we'll get there. So at the moment, what we're doing is this is still pseudo-logical form. So there's still this is halfway between the sentence as you'd speak it out loud and the actual way that a symbolic logic would represent that same idea.
Yes. Okay. So I thought it was a bit surprised by that it was that format. Okay, great.
Yeah, because what you've pointed out there basically is that the first premise, if P then Q or R, is ambiguous. Just hold that thought because we'll come back to it. And ultimately, what we're going to be doing is spelling this out in mathematical rigor that would be acceptable to a computer program, provided it had the right syntax built into it. Okay, so it is computer programming.
I thought it was. That's what I was surprised by it. Yeah.
Yeah. Okay. Cool.
It's really good. I can't wait. So let's keep going.
all the tension.
Yeah. So what we're going to do tonight in this bit, we're going to be looking at the connectives and arguments and how to express the logical form of an argument with logical connectives, and we're going to get on to Helena's favourite thing, truth tables, a little bit. So to begin with in this propositional logic, what we're interested in is binding those logical atoms with these 5 different words or connectives or operators. So there's 4 of them are binary. That means that they connect together 2 propositions, and one of them is monadic, which means that it sticks itself in front of a single proposition. So and, or, if, then, and if and only if are binary. And not is monadic. So
does everyone understand what that means? Binary versus monadic. And maybe you should just sort of quickly explain that. Binary 2 and, let me let you do it.
Well, I think it will make more sense in a minute. So if we just, even if it's not quite, binary, so if you say like P and Q, obviously you need to have 2 propositions, one on each side of the and. With not, you could just stick a not in front of P, like not P. It doesn't need a Q as well, right? So it just sits in front of one thing. The other 4, glue 2 propositions to one another. Right? Not just changes the truth value of one of them from whatever it was to the opposite truth value. This will become much more clear in a moment. So, what the hell am I talking about in here? Well, some of the usual meaning of these words, wasn't it?
That's just about universe of discourse and no, go ahead.
So I can't think for the life of me what I was trying to say with this umbrella example right now.
Oh, it's the reason is because there's a possibility of equivocation, right? All lemons are yellow. My car is a lemon, therefore, my car is yellow. Well, things like that. You have to make sure that you specify what those words mean. The word lemon in one context means a car that's prone to break down. In another context, it refers to a fruit. So you have to make sure that you specify in your universe of discourse or your dictionary or your legend exactly what we're talking about here and how the words are to be used consistently to avoid equivocation. I think that might be what you bring up. Because
in this example, I went outside and opened up my umbrella. The word "and" there isn't really. I mean, what it means is I went outside and then the next thing I did was I opened up my umbrella. Right. So it's an "and" as in a kind of like subsequently meaning.
Chronological thing.
Yeah, exactly.
Yeah. In
this logic, it's not ever going to be meaning "and" in a chronologically and then such and such. It's going to be completely defined in such a way that it's just gluing 2 propositions together. What it does will be a product of the truth values of those propositions that it glues together, and that's it. So I guess one of the benefits, one of the things that's really nice about logic, one of the things that you grow to love about it, is that everything is perfectly clear. There's nothing, there's not like when you have conversations with people where you're coming from vastly different perspectives, and you can sort of just be talking past each other, and it's quite frustrating because who knows whether we're really disagreeing with each other. Maybe we're just so different that we can't blah blah blah. With logic, that it's going to like eliminate all of that ambiguity, all of the worries about different ways that you could understand these words or that words or whatever. We're going to precisely define everything that we're going to be using, and what we're not going to be defining, like those atomic propositions, we're just going to abstract them away so that the only thing that's important about them is whether they're true or false, and we won't care what they actually mean. The logical words where we care what they mean, we'll be defining them completely and utterly precisely so that there's no ambiguity whatsoever. And if you don't like ambiguity, then you will like logic. I think that's what I liked about it anyway, was that you can, it opens up the possibility of being able to actually prove things and actually say things definitively, which is sort of rarely had in philosophy otherwise. Anyway, of what people saying they want me to increase the presentation size.
Do you need to be able to see the thing on the left-hand side? If you move that to the left of your.
So if I do slideshow, does that make it bigger? Has that made it bigger?
I think
it hasn't done anything yet. It's just
the easiest thing to do, Alex, would be to X out your outline, and that'll give you more room to put the slide, presenting the slide on its own. The X on the left-hand side at the top, where
up here?
No,
lower.
Down there where those
Lower.
are on the left.
This.
Yeah,
Right. Yeah, got you.
now you can present it bigger.
Okay.
Yeah, you're also going to need to remove click to add notes to also make it bigger.
Yep.
Or I have an idea. See, this is a monitor, fella. Say stop using laptops. Here's a real monitor.
How about? No, that hasn't done anything. All right, that's about as big as it needs to be, right? I think presumably everyone can see that.
We're not seeing your slide right now. You're not being presented.
No, really?
You're not screen sharing.
Yeah, you're good there.
Say what?
My
Screen share,
monitor
I'm not
is
getting paid for this.
big.
It says I'm presenting to everyone. All right, let's try this again.
There it is.
Yeah.
Oh,
Yeah, everyone got that?
Yeah.
Alright.
Your
seeing
only
it now.
other option is to make the
There
font
we go.
1 or 2 sizes bigger, because the white itself won't change unless the font gets a little bigger. That's his only other option.
If you can remove the click to add notes part, that'll
Yeah,
probably do
that
it.
would help.
Yeah,
Yeah,
There we go. Yeah.
Okay, cool. All right.
I'm sorry.
so
Well, hold on. It's way too big on mine. Can you shrink it back down again?
Shut the fuck up, JD.
Sit further back.
Yeah, come on, let's go.
I've
Alright,
never
cool.
had a chance to say that.
So let's start leaving behind normal words in English and start treating things in symbols altogether, right? So these are 5 symbols which are the connectives. So in order that you can see my cursor, right?
Yep.
So that's and, that's or, that's if then, that's not, and that's if and only if. You'll come to know these things as we go along much better. If we were doing this as an actual course, I'd be saying that they'd become your best friends and you get to know them loads, but I guess you just become
These are
more
really
familiar with
fun.
them.
These are super fun. I love going through this. Right. So, all right. So, does everyone get that? So, the up caret is and. Right?
Yeah.
It's a conjunction. The Americans will know this. Conjunction, junction. What's your function? Hooking up phrases. Blah blah blah.
Yeah,
Right.
you're overestimating Americans a little bit.
No. All right. So then the down caret.
Yeah, so that's conjunction, and then let's just show on each side of the and are what we call a conjunct. So you might say, you know, the conjunct on each are true, therefore the conjunction is true. Conjunction meaning the whole thing, right? Anyway, so yeah, the down carriage is disjunction. That means or. On each side of that would be disjuncts. And negation in normal parlance, saying not whatever it's attached to or whatever is not true basically means the same thing. You just choose whichever way you want to say it. So yeah, that's negation. Conditional, if then or implies, and then biconditional, just meaning if and only if, and it's often written like this, if with two Fs, just for shorthand. So if and only if is really just an if then running in this direction and an if then running in the other direction, exactly what the picture demonstrates. So there are other ways of writing these same symbols, but these are the ones we're going to be using from now on. So let's go back to our argument then that ran like this: if God knows the future, then humans have no freedom. God knows the future, therefore humans have no freedom. And we said that that had the form of if P then Q, P therefore Q. Well, now we can add, it would be written like this: so P arrow Q, P, and then this bar underneath it is called a solidus, meaning the therefore Q. So if P then Q, P therefore Q. So that's basically the logical form of this thing, which is like the pseudo-logical form of this thing, which is the argument written in English, or how you might hear somebody saying it. As to see another one, this is a previous argument that we had before. If the coin landed heads, then Bob won his bet. It's not the case that Bob won his bet, therefore it's not the case that the coin landed heads. And we saw that as if P then Q, not Q, therefore not P. Well, that turns into this: if P, therefore Q, not Q, therefore not P. So anyone who's listened to me talk before has probably heard too much of me saying not P, therefore Q, whatever.
Only for about 2 hours or so.
No, we love it. We love it.
Yeah, well,
moving on.
I don't think the blame for that lies on you, though.
All right, so here was our other one. If Chris drank tequila, then he went crazy, or he fell asleep. He didn't drink tequila, blah 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 blah. So we would have this now written out. I suppose I've introduced these brackets without properly saying who they are, but they're also a part of the notation. So now we're saying if P, then brackets either Q or R. Not P, P and not R, therefore Q. So now we've got something which is not ambiguous, right? This first thing expresses a definite propositional form. Before it might have been that if P, then Q, or R. Right, that with the brackets were like here and here, but we've spelt out exactly which way around it's supposed to be out. This is ambiguous between the two readings. This isn't ambiguous. We're going to get even more precise in a minute about how to do this
I would
properly.
like that, yes.
Okay.
I'm still not completely happy with that.
Okay.
So I'm surprised that you're not even happy with those parentheses.
There should be outer parentheses really on the whole thing. Then it would be shipshape.
Yeah. So would you agree with that, Rumpus?
Well, this isn't how a programming language would work. You can't the result has to be one specific thing. You can't, because the or, you see, that's ambiguous. I would say that was ambiguous because you could have one or the other. So you're not defining a fixed state. There's no necessary consequence. Whereas
so you're talking about, well, is this an inclusive or an exclusive or?
Right.
What
That's
do you mean by or, that kind of thing?
that one, it's an inclusive or that you got there. He hasn't mentioned exclusive or so far.
Right.
That's
right.
Yeah.
Well,
All we use is inclusive or in this form of logic.
Yeah, exactly. Yeah.
Yeah. Whereas in programming, you normally, well, you can write in programming languages that have inclusive or exclusive or
Yeah,
or
we
both.
normally use inclusive or as well. Yeah.
Right. Yeah. You can have a richer system, but it just has to be said that this is one notation. There are different systems of notation. The notational system is somewhat arbitrary. It doesn't have to look like this. It could be expressed in a different notation. It would come out looking completely differently, and it would be the same thing. A lot of people are going to be used to Boolean algebra. A lot of people who are programming know about Boolean operators, right? That's what this is. You're just looking at it expressed differently. It's exactly the same thing. People who know Boolean algebra often come to this kind of form of logic and go, I already know this.
Yeah.
Exactly.
And there's a sense in which they absolutely do know it. They really are the same thing.
Yeah.
Okay, cool.
I know for me, I get stuck in the wording. When I see it written like this, I get it. I understand how it works. But when it's just words and concepts, it's very difficult to put my finger on what's actually going on and what they're actually saying.
That's very
interesting. So he's going to
I have
explain
the
how to do that with his numbering system, or I suppose it's the numbering system, right? Which is really going to help a lot in terms of translating a bunch of English into these symbols that are easier to work with.
Yeah, the symbols I agree are easier to work with as well. They're more precise, and like Ozzy, I'm with James on this one. Looks more precise to me, although as I say, I'm not entirely happy with the conclusion of something being one thing, or it's not. You haven't specified, but yeah, as you say, it's a different system where you can.
It'll make sense to you in a minute, I think.
Great.
But if we're just to come back to the comment about like turning the English natural language stuff into this type of form and then into this type of form, it is a bit of an art rather than a science sometimes, certainly to begin with, and it depends on the way people actually say things. So even this is quite artificially regimented in the way that I've phrased the argument. It's easy to translate it into this because I've said it in a specific way, and obviously once you go from there to there, it's easy. But often when you're reading a philosopher or reading a newspaper or listening to someone debate you on YouTube or something, the actual English that they say will be much more disjointed, and half say something, then stop mid sentence when they've thought about it a bit more, start again, blah blah blah. So it can be quite difficult, but I suppose it's key to try and track back, and if someone's saying something to you to say, so what are you saying this? For such and such, try and break it down into propositions. Basic atomic parts that on their own should be considered true or false, and ask about, well, is this the logical relationship that you're suggesting? Are you saying if this, then that? Or are you saying either this or that kind of thing? I'd try and get someone to assent to the basic logical structure that they're saying. And there are other more complicated logical structures. We're not going to be dealing with quantifiers or variables or constants.
I was looking forward to using quantifiers.
Well, we will do that next time, but this time we're just going to be looking at propositional logic.
Even juicier.
Yeah, so propositional logic forms the core, the most simple type of logic. And in then first-order logic or quantified logic is just going to be a predicate logic. It's just going to be an extension to this. So we're going to be adding houses onto the street that we've already built. But this is the first bit that we have to get through.
Because of course you use quantifiers in your your last Matt Slick thing.
That's true.
Thing.
So we'll go through them in more detail. It is going to get a lot more complicated by the time.
Yeah, let's keep plowing through so we can get to a little bit of meat this time around. So people will join us next time when it gets really meaty.
So the way that we're going to talk about these, the binding elements, the connectives, is all about they're going to be called truth functional connectives, and that means that the molecule that they make has a truth value, and that's the product of the atoms that they bind together and which particular binding it is. So when we speak about the truth conditions of a sentence, what we're saying is in the circumstances that makes it true or false. This will be clear. So A and B is true only when A is true and B is true, and in any other case, A and B is false. So in order to code this out so that it's very easy for everyone to see, we're going to draw a table which has all of the options in it. Each row of the table we're going to call a truth assignment, and that's going to be showing you the truth values of the atoms A and B. And then we're also going to show how that factors in to the molecule that we've made and the truth value of that. So here's our truth table. So on this side, these columns are going to be the truth values for A and B. And then this side we're going to have the truth value for the molecule A and B. So first of all, if A is true and B is true, then the molecule that it makes A and B, that's also true. Right? That's what A and B means. It means both of the things that it's sticking together are true. Right? In the other cases where A is true and B is false, then the overall molecule that we've made is false as well. It's not the case that if you say A and B, but B is false, then it's not true to say A and B. Right? So that any other combination that we can put together makes the molecule false as well. It's only true when both of the things that it glues together are true. So now what we've done here is effectively defined and in terms of it's a product of the parts that it glues together. Right? It's true only when the bits that it puts together are true, and it's false in every other case. And that's it. That's all that there is to and. So we're just saying it's truth functional what it does is it's a product of the truth values of the bits that it glues together.
So,
Sorry, Ozzy, what were you going to say?
Oh no, no, please finish.
Okay, so each of these rows along the side are truth assignments. So we're saying a truth assignment is true, true. Another truth assignment is true, false. Another one is false, true. Another one is false, false. So by running through all of these are all of the possible combinations of truth values that these two propositions can have. And what we've done is catalogued the behavior of AND for all of the possible different ways that the things that it glues together could be combined. So we've exhaustively defined the behavior of AND. So that's it. That's why I'm saying that's all that there is to AND. There's nothing else to it. When we said before, when you say I go outside and I open up my umbrella, there's like another sense of AND. We're not worried about that type of AND. This is what AND means. This is the definition of AND. Nothing else to it. So yeah, sorry, what were you going to say?
I was just going to say, so one way to understand this is what we're doing is we're expressing formally the meaning of the word "and." Any sentence of the form Johnny went to the store and Sally went to the store, when would it be true? Under what possible circumstances would that sentence, Johnny went to the store and Sally went to the store, when would that be true? Well, it would be true just in case that Johnny went to the store and Sally went to the store.
Please don't use just in case.
And, well, okay.
Oh, God.
I'm sorry, that's perfectly acceptable grammar, again.
Oh, it's just in the case.
And just in case. Okay, so, but I don't want to detract from the point here. So the idea is one way to read these horizontal lines, true, true, true. You can think of these in terms of possible worlds, right? Imagine a possible world where the proposition A is true and the proposition B is true. In that possible world, where both of those are true, that "and" sentence would be true. But in all the other possible worlds, where one was true and the other was false, or one was false, the other was true, or both were false, in all those other possible worlds, that "and" sentence would be false. So that's one way of understanding this. I hope I haven't left ahead there.
No, I think that's fair enough for me.
I think it's great that you're doing that because we're going to get into possible worlds later. So why not start now? I mean, it counts now too.
Okay, so the reason that this is truth functional then is because the truth value of any "and" sentence is determined by knowing the truth value of the conjuncts. Each of the conjuncts, that's the A and the B, the truth value of the conjuncts determines the truth value of the entire conjunction, the A and B sentence together. And you can do it for every possible combination of true and false for all of these. And you could even have a sentence that was a conjunction like A and B and C and D and E and F, right? Johnny went to the store and Sally went to the store and Amanda went to the store, and you could do for all of those, and you could still determine the truth value of a very, very long conjunct or conjunction as long as you knew the truth value of all of the individual conjuncts along the way.
That's it. Okay, so let's right. So yeah, blah blah blah. So. I don't know, this is me just then spelling out that, again, this second one has the word "and" in the sense of subsequently rather than the sense of conjunction. So we would say Ned is happy and John is sad is correctly formalized as P and Q down here. One falls from Ned and John will shoot means one falls from move and then John will shoot, or if there's a move from John, then Ned, then John will shoot.
If you get "then" instead of "and," that would have been better, yeah.
Yeah, so it's incorrectly formalized as P and Q, even though the sentence has the word "and" in it. So just to be clear, this is the sense of "and" that we've just defined, not this sense of "and."
Which is to say that in natural languages, words like "and," the connectives, words like "and," are not always used as logical connectives. They're sometimes used in another sense, as we were seeing in the second example.
That's right, yeah.
So they're ambiguous, and so we want to make sure that when we translate natural language sentences into formal propositional logic, that we're not just seeing the word "and" immediately subbing in that symbol, because it might not actually be a logical connective. It might not actually be used in that sense as a logical connective.
Right, because in natural language we often drop the "then," right? We just say blah, 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 and blah, 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 but what we really are implying is blah, 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 and then blah, blah, blah.
Well, yeah,
So
but
we
the
wanna
trouble
be
is the
careful.
and is equivocating, isn't it? It's not just the then. The missing the and is actually it can mean two different things. It's just
That's
that
it.
then helps you to understand which and you mean.
Right.
Exactly. So if you're going to do the translating thing, you can't just do it sort of mechanically, I don't think. I think you need to look at the natural language and see, does that and really mean and then? And if it means and then you got to do something else, which we'll talk about later. But if it only means and, then you can use this form. You can use the up caret, meaning the conjunction.
Yeah.
There's a but here, and the but is that the word but usually means and. If I were to say Ned is happy but John is sad, that just means Ned is happy and John is sad, right?
Yeah, it's true in those same circumstances that
Right.
Ned is happy and John is sad is true. So as far as its truth value is concerned, they're equivalent to each other.
Right.
It has some kind of like
but is
emotional
correct.
value different.
Yes, but yeah, but has different connotations, of course. But the way it functions, truth functionally, is that's redundant. But the word but operates or serves as an and in most natural language cases.
Yeah.
And so we translate but. Very often we translate the word but as and in propositional language logic. Sorry.
Okay, good. So let's crack on. Here's exactly the same idea. Here's the truth table for or instead of and. It's false when, so A or B is false when neither A nor B is true, when they're both false. It's true when A is true and B is false, although that's this is written the wrong way around for this, but you get the meaning. When one of them's true and the other one isn't, the overall molecule is true. And also, if the other one is true and this one is false, then this one's true. All it needs is one of them to be true, basically. What about when they're both true? So here's the difference between an inclusive and an exclusive or. An inclusive or, Kennedy opposed the bill or Campbell did. That would be true if both of them opposed the bill. That's what this means in natural language. Exclusive, or we say either Miliband will win or Cameron will win. They can't both win. It means one of them will at the expense of the other one. So if that was the case, we would define or, exclusive or, with this top row being false when they're both true. The way we're going to be doing it from now on is that it's true when they're both true. And that means what we're talking about is an inclusive or.
Well, I'm a little bit surprised you use the same symbol then. There's usually a zero with a line going through it for the exclusive or.
I would do, but this is the only time I ever mention it. So just to say that if you wanted to define this symbol as an exclusive or, you would just say that the top row is F. If you want to define this symbol as an inclusive or, you would just say that the top row is a T instead. So yeah, strictly speaking, if you want to have these as two separate symbols, I mean they have two separate meanings because the truth assignments give you different truth values. So that we would, to avoid ambiguity, we would have to have some other symbol in here. That's true.
I think there's a little line or something you put across it, isn't it, or something like that, for an exclusive version of that, I think, actually.
There's loads of different ways of symbolizing it. Yeah, an X in a circle is one way of doing it.
Yeah,
But
that's the other one, yeah.
we could just get this by sticking a bracket around here and putting a not in front of it. I don't know. Damn it, this isn't as clear as it could be. But not A and or B is the same. It is an exclusive or, basically. That would now give us that this truth value is false. So my point here is just simply that we don't need to have two symbols. We can just have inclusive or, and when we want to express an exclusive or, we can just negate that, and it would be the same.
Well, only for that, yeah, but only for the truth case. You couldn't put the table of what you did because it wouldn't then operate correctly for the other ones.
Yeah, I suppose that's true. Yeah, I'm just saying if you wanted to express when it's.
In the case of the true, yes, but this other you couldn't change what you did wouldn't be valid for all of the things in that column then.
No, it wouldn't be valid for these other truth assignments. But
Yeah.
if we just wanted to capture what it would do for this truth assignment, we could
Yes, just for that one, yes.
And in fact, we could just generate it with negation for all of these if we wanted to. There's nothing that we can't do with inclusive or and negation.
Alex,
To mimic an exclusive or. Yeah.
could you, I'm not understanding how A and B in the second set can both be true at the same time. So could you use another example? Because if it's true that Miliband will win or Cameron will win, how can you then say false? I'm not quite understanding the difference between the inclusive and the exclusive.
So what I'm saying in this case is, so you would say when there's two people running, say Hillary or Donald running, right? That either Hillary will win or Donald will win, right? That's but the way that you mean the or in this case is in an exclusive sense.
Oh, I see. I get you. Yeah, that makes more sense. Yeah, I get it.
Right.
Okay, that's good. Thanks.
Yeah,
Okay,
I mean,
so,
I like that, Alex, actually, because that's the first time I've actually seen exclusive or used in natural language. I'm used to using it in just in the symbols, so that's an interesting presentation there, actually.
Okay, good. So in natural language, we often slip between the two of them. And in fact, actually, I think in natural language, we most often would have need to say an or statement when we're saying now, only one and not the other is the case. But I actually found it more difficult to come up with an example for an inclusive or that was a plausible natural language sentence. Yeah.
Oh, right.
But in logic, anyway, the one that we need to pay attention to is this truth table here. So from now on, or means only false when both rows are false. And in a sense, it's kind of like a mirror image of and that we had a minute ago, which is only true when both of them are true. So they kind of represent a sort of inverse image of one another.
Right.
Are you going to show the tables to get the and the ors together at some stage? That's I think that's very illustrative for people who are not familiar with this. The difference between the or and together on the same screen.
I think there is a slide at the end which has all of the truth tables on at the same time. Okay, negation. This is really easy because, like I said, negation just sits in front of a single proposition. So the truth assignments, all we have to do is consider the truth values at A when it's true and A when it's false.
Wait, hold on, now I'm totally confused. I'm lost now. What's going on there? That's just all kinds of weird squiggly things. And this is just nonsense. I'm getting out of here.
So when you negation just sits in front of a single proposition, so it's monadic rather than binary. So what it does is the molecule that it makes. This is the molecule that it's made out of this A being the atom. And the molecule that it makes just takes the opposite truth value that the atom had. So if A is true, not A is false. And if A is false, not A is true. Right? It just toggles the other truth value. That's all that it does. Does that make sense?
Oh, yes, that's very clear.
So it's just the word not. What does the word not do? It just negates whatever the proposition is. So if the proposition is there is a God and you stick a not in front of it, then what you're saying is, if the proposition is God exists, then sticking a not in front of it is simply saying it is not the case that God exists. God exists not. Right?
And while you're on that subject, I just want to point out the difference between not of a proposition which has a truth value and saying not something. Like saying not God is not the same as saying not God is real. But God is real has a truth value, and saying not God is real is quite different from saying not God.
Yeah, not God is just not God is just sloppy, I guess.
Yes, I mean, what is not God? That's a set operation. It's like saying what is the thing? What are the things that are not God? And that's a huge set of things, as opposed to not a truth proposition.
Yeah, connectives these are propositional connectives. They connect propositions, not names. You can't
That's what
you can negate a sentence that expresses a proposition. And so this is just a connective that works on a single proposition. It doesn't conjoin two or more propositions the way or does, or and does, or if then, or if and only if. It works on one, and all it does, as Alex said, is it toggles the truth value. It just switches the truth value. If the proposition has the truth value of true, and you stick a not in front of it, it becomes false, and vice versa. If the proposition is false, then sticking a not in front of a false proposition makes it true.
Yeah, so this should be the easiest one to understand. I think maybe I should have started with this one, but whatever.
I have so many jokes I want to bring up about previous conversations, but I'll let them slide for now.
Okay, cool. So this one is probably the least intuitive one, and the one that most people have issues with, and there are even philosophical issues with this one. Mm-hmm. Now, the most intuitive truth assignment is this one. So if you say if A, then B, right? What it's saying is if A is true, then B is true. Now, if A is true and B is false, then when it said if A is true, then B is true, that must also be false as well, right? Because A is true but B is false. So it seems like it's obvious, most obvious, that the condition in which this is false.
I was thinking of doing a video on this very thing because the way I worked it out is the reason those things are question mark is because they're dependent on the possibility of another third state. Because in other words, you don't know that something else is creating B. In the other cases, I think if it's a three-state gate, and I don't know whether I'm sidetracking here, but I think I can make a very conclusive intuitive, because it took me a good week to understand exactly this very thing. But I'll possibly shut up.
It's all right. But for the purposes of this, the conditional, the if-then, is the kind of technical name for it is a material conditional, and it's like all of the rest of these connectives. It's entirely defined by the way that it produces a truth value based on the truth values of the atoms that it joins together. So we just say that it has this pattern, right, which is that it's true in all cases apart from this one. Okay, so there are problems with this when you think about it. Obviously, well, if A and then B is true when A is true and B is true, that's fair enough, you know. If I'm speaking, then you can hear me. It's true that I'm speaking, and it's true that you can hear me. So then, okay, it's fine to say that if I'm speaking, then you can hear me. That makes sense. This one is a lot less intuitive, right? If it's false that I'm speaking, but it's true that you can hear me, we still say that it's true that if I'm speaking, then you can hear me. It doesn't really fit with the way that we speak in natural language. It's just an artifice for logic.
That's the one that pisses me off.
Yeah, that hangs everybody up. That hangs everybody up when you're doing this.
My first thought when I saw that was, isn't that affirming the consequent? But I guess it's not.
It's not, because so the difference there is that affirming the consequent is it's a type of argument, is that you're deducing the antecedent from the consequent. Here what we're doing is we're sort of going the other way around. We're showing you that the connective as a whole, the molecule, is true in the case where the antecedent is false and the consequent is true. But I'm not concluding that the antecedent is true by affirming the consequent. And it looks very similar. I can see how it's similar.
I get it now. You have to kind of tilt your head sideways and hit yourself a few times. I'll get it. Just give me a sec.
All we have to think about this is it doesn't really model the English sense of if-then, right? It's just a technical operation that we can do. It just combines these in such a way that it's only false when the first one is true and the second one is false. And in any other circumstance, it's true.
Well, from my limited understanding of this, you're trying to determine whether B is true or false. Is that not how that is reading?
No, you're trying to determine the truth value of the entire sentence if A, then B. Under what circumstances is a sentence of the form if A, then B? Under what circumstances is such a sentence true and false? And when is it true? In all circumstances except the second row.
Okay.
Okay. So that's the way to understand this. One way to think about this is kind of like on the analogy with or, inclusive or and exclusive or. We have two uses of the word or, right? And one is more restrictive than the other, right? The truth conditions for exclusive or are more restrictive than the truth conditions that define inclusive or. Think of this as a more artificial and restrictive usage of if-then than we would use in natural language. In natural language, we would not use, or actually this is a less restrictive usage of if-then than we would use in natural language. This is a more open usage of if-then than we would use in natural language. But there are logical reasons why we go with this, but that's looking ahead.
Yeah, so what we do in
the form of a sentence, in any way, shape, or form that makes sense?
So yeah, I think of this. Oh, go ahead, Ozzy.
No, you go ahead. I think you had an example to give there.
No, I didn't have a very good one. I'm just sort of I'm going to make a very general sort of thing. It's like when you're trying to teach, you know, in math or algebra to beginning students, and you're trying to explain intuitively sort of how the negative can be direction. And it's easy to do in every case except for the case that negative times negative is positive, right?
I
And so
understand that.
you explain intuitively all of them, and you can say, well, look, if you're going under the water and then you go under the water even more, you're going to be more negative, right? But when you get to negative times negative is positive, you have to throw all the intuition out of the way, and you have to present a sort of, look, it can't be this one because that's covered. It can't be this one because that's covered. Well, it can't be this one because that's covered, so it must be that a negative and a negative is a positive, right? A negative times a negative is a positive. And so you can't do it intuitively, but since there's only one case where you have to do it deductively, it's easy to explain that to someone who's just learning about the fact that sign can indicate direction. So to me, this is kind of analogous. It's like, here's the one thing where you can't do it intuitively.
You see, the way oh god,
I was just thinking, I was just thinking, like in the mathematics, like it is counterintuitive. I really thought about, like, if two, positive and a positive times positive is positive, then obviously a negative times negative is negative. Like, well, no, like, but again, you start tilting your head, going, and it's the way it is, but it's kind of hard to wrap your head around it.
Well, the thing
you
about
can't, you can't do it intuitively.
negating
You have to explain all of the other cases intuitively, and then go pretend that you're someone who was just inventing this. Okay? And so now you've got an intuitive explanation for all of them, but now you've got this negative times a negative. Well, if you declare it to be a negative, you're going to have a lot of problems with all the other ones that you just did intuitively. So it's got to be, because of the fact that we've explained intuitively every single case except for this one, let's just agree that we're going to call it positive.
It's not.
It's not exactly right that you're just agreeing, because there's real proof for it, but it's not the same kind of proof as an intuitive proof.
Yeah, I don't think that works here, because there's the negative is a lot easier to understand than what you just presented. But that's okay.
So there's certain things that we let's just get this out of the way, that to some extent this is just a purely formal symbol. And to the extent that it bears relation to the phrase if-then in natural language is only partial. And there is in this series there is an entire lecture on this material conditional, the paradoxes associated with it, and the way that other ways that people can think of formalizing.
So you will come back to this, and we will.
Yeah.
Okay, that's fine. Then let's just keep moving. Let's keep going.
I got one little contribution. The way I've worked it out to be in terms of logic gates is that you have to consider the possibility that not only A is causing B. So, for instance, although A does cause B, there could be something else, a third thing that could be causing B. So, for instance, if you regard B as it being wet, you could say that A causes it's raining. A could be raining, and B could be whether it's wet. But there's another thing that could be causing B to be true. That is, you flooded the place, and that isn't allowed for in this column. And I think I can make a very good case for saying that's how it works. There's another potential state that's not in this column that can make B true. And so
What's so hilarious about what you've just said is I kind of came to the same conclusion, but I did it thinking about Minecraft and Redstone.
Well,
I guess it's these logic gates in some kind of way, right?
The geek emerges.
I'm going to make a big one on this if Alex is well, of course Alex is probably going to explain it properly in his whatever it is.
Yeah, so I think Alex is going to get into this, but for now let's just all agree, okay, we're going to allow this assignment, and we'll explain it later, because we got to get away from A and B and back to P and Q, because I think one of the biggest things is people don't understand, why are we talking about A and B? This was about propositions, and so I want by the end of this to make that connection so people can understand why we are going into these A and B's and how they're going to relate to actual propositions.
Well, they're just the same as P and Q, so how are they different? I don't understand your point.
Well, so the reason I've used A and B rather than P and Q is simply just that A and B could stand either for atomic propositions, or they could stand for formulas themselves that are more complex. So A, capital letter A, as distinct from lowercase letter p, means that A could be a sentence which is itself a sentence P and Q. Right? As long as that's true, as long as P and Q is true, i.e. the formula A, that's all we need, that's all we care about for determining the truth value of the overall larger molecule that we're looking at. So
I think it
it's
helps
like
the most.
levels of structure.
This is one of the ones where I think examples help the most. Like the more
Well,
times you
let's
put
wait.
this in there,
Let's wait on the examples because we need to get through exactly what Alex just said now. And so I think we're really close to getting to the examples.
So yeah, and before I move on, if you want another way to think about what if A then B means in this context, like what's this operator expressing? And unfortunately, I'm writing this on a Mac instead of a PC where I first formatted it, and I don't have the right negation or conjunction symbol. But this just says the same as what this says. It's saying it's not the case that both A and not B. Right? Now that's just to say it's not this row. Right? This thing is true so long as it's either this assignment, or this assignment. It just rules out it being this assignment. So if A then B is true, it just means that it's not the case that A is true and B is false. It means it's one of these other situations. So that's just to say not both A and not B. I don't know if that's clearer, but these two things are equivalent. This and this are equivalent to one another.
It's clear enough to get going on it. So
Cool.
we'll come back to it. I can accept it the way it is.
So yeah. So
there's a way to show.
Am I right that he just said that it's the same kind of thing as saying it's not the case that A is true, and B is false.
Yeah.
Yeah.
That's right.
Okay. Does everyone follow that?
So there's one way that this is false, and it's when A is true and B is false. So if this is true, we're ruling out the case that A is true and B is false. But we're not saying what else is true. It's one of these other situations. That's it.
Yeah.
Anyway, let's not flog this pony too much. I've got about 15, maybe 20 minutes for most. So let's crack on and see if we can. We'll certainly finish this slide. Here's the biconditional. This is the final one of the 5 propositional connectives that we're looking at. So this is true. Basically, the easy way of thinking about this, it just says that these two have the same truth value as each other. Right? So it's true in circumstances where they're both true. Like if A, if and only if B is true when A is true and B is true. It's also true when they're both false. And if one of them has a truth value that the other one doesn't have, if A has a truth value that B doesn't have, then A, if and only if B, is false. This is also called an equivalence relation. So it's saying that they're equivalent or they have the same value. So think about this as the same value relation. It just says that A has the same value as B. It doesn't care whether A is true or false. It just says that A and B have the same value as each other. So if they have a different value to each other, then saying that they have the same value to each other is itself a false thing to say. Does that make sense?
Yep. It's a knotted exclusive OR, isn't it? It's
not an exclusive OR.
Yes, a knotted exclusive OR.
A knotted exclusive OR.
Yeah, knotted. If you took the exclusive OR operation, then you knotted it, you would end up with that.
Okay, great. I didn't know that terminology. Okay, so what we've done now then is we've got these words and, or, if then, not, and if and only if. And we've seen how we can glue propositions together with them. And we've shown how we can express those logical connectives with these symbols, the up pointy, the down pointy arrow, this negation thing, and the double pointy arrow. And they're the propositional connectives. They kind of can capture the usual sense of or and not and if and only if. They don't really capture the usual sense of if then, but it kind of gets somewhere towards them. And we've shown how we define these things in terms of their truth conditions. So what this does when it binds two propositions to one another is entirely dependent on the values of the things that it binds together. That's all that it does. So that means that it's a truth functional. We look at the truth conditions and we can write them out in a truth table, and that tells us the behavior, exhaustively defines the behavior of this operator. So I think instead of starting the next lecture, then we just leave it there for the time being, because I've only got about 10 minutes realistically before I need to get going.
Okay, that sounds good. We'll stop here and we'll start again next time from where we just were.
Yeah, so maybe we can have, are there any questions about any of that, or any comments or feedback? Or
I think it's excellent. I thought it was really very good, Alex. I really enjoyed that. That was absolutely brilliant.
Thank you so very much, Alex, for taking the time and helping us lesser creatures get a handle on some of these. Like, we hear this stuff all the time. We know arguments are bad, but we don't know why, and we don't understand enough to address these issues in a way that, okay, this is how you address that. This is how you address, and stuff like this is what we need to be able to make better arguments. As we all, we defer to Ozzy, who always complains about the bad arguments being made on YouTube.
Well, I do try to explain why I think they're bad, but I have a question for Alex. This is a softball because I know you know the answer, of course. Where does this come from? Where did truth tables come from? These truth tables that we're doing, like, who originated them? And can you say a little bit about that?
Yeah, so the truth tables, the idea of writing out the truth assignments on the one side and then giving the values to the formulas on the other side, putting it in that way was developed by Wittgenstein. And the story goes that it was when he was a stretcher bearer for the Austrians or something in World War I, that he's supposed to have been jotting this stuff down, like, in between artillery onslaughts or whatever. I don't know whether that much is true, but it's certainly that notation, the idea of drawing out the tables like that, was developed by Wittgenstein.
That was Bull, wasn't that Bull then?
Certainly not.
Okay. No.
Bull does make some developments, and Bull's contribution is that he builds the calculus so that the combinations of variables can always take on either one of two values, truth values. So he calls it like the 0 or 1 in Bull. That stops it from being an algebra like mathematics, where the values of an equation would be like a number or something, so it can take on like any value between like whatever 0 and infinity or something, where in Boole's contribution is to develop an algebra so that the answer, if you like, to any equation is either 1 or 0, either T or F, true or false. So that's what he contributed to the history of logic. Well, there's some other things as well, and there's no need to go into them now. But the idea of drawing the truth tables like that is something that Wittgenstein added, even though the behavior of the formulas had already been fully worked out and formalized previously. People weren't drawing them into a table like that beforehand. So, like with most developments in logic, it's kind of notational. It's not that interesting, but actually it's really significant, and that's all that there is. It's developments in notation in logic. So, like, if you don't get excited by innovations in like squiggly lines and how we draw things, then you're in the wrong business doing logic. That's all that there is to this, really. So I'd be happy to talk in more detail about the development of logic from like the earliest years through to how we get to this calculus that we're doing now, the propositional logic and the first order logic, because it's got an interesting history that involves loads of like really cool and sort of extroverted characters, and they all do different things and stuff like this. It's a fascinating story. I'm not going to start that story now with like 7 minutes before I have to go and eat, of course. But I'm actually editing a book on the history of logic, which has been ongoing for about 5 years, but it is supposed to be coming out this year. So there'll be some extra resource people can go to if they want to. And I'm happy to share the full series of slides with any of you guys if you want it. So you can just
I would love that.
Yeah. Okay.
No, you guys don't get that.
Sorry, I'm not prepared to do that. Sorry.
When I started my IT career, we were working with DOS 3.1, and so
I remember those days.
Yeah, it's like I remember all this terminology, but couldn't connect it to the logic that I hear about. But as soon as you start presenting it, like, oh, of course, I get it. That's the logic of computer language, and it can't work any other way. It has to be that way.
I mean, it's amazing to think just those tables that Alex presented, the and, or, and the not, with those three things, you can do everything you need to do in the processor chip. It's incredible.
That's it.
Absolutely.
So I think we should make this the PowerPoint things present shareable or whatever the word is after we've gone over them. right? So like
Okay, yeah, fair enough.
we went all the way through lecture 3. Is that right?
Yeah.
Yeah. So I could make those shareable, or you could make those shareable up to 3. Actually, the truth of the matter is I don't care. You can make them all available now if you want. Right?
Up to him, I think.
So
We
I
already
take
got-
back everything I said.
We already have one book to read, Helen. How much more reading do you want us to do?
Oh, you haven't seen these PowerPoints. They're just unbelievable, really fun. All right, so I think we should, since Alex has to go eat, if there's anything you want to say, you know, let's say it, and then I think it would be fun to sort of practice a little bit if people want to stick around. And so, Alex, if it's okay with you, I'd like to use sort of the first several examples in your quiz. I think we can go that far, at least with some of the super easy ones. We could probably play with those. Would that be all right with you?
Let me just have a look at them, because it's been a few years really since I've gone over this in any detail.
So those are sort of, here's a sentence in regular English, and make a dictionary, and do the notation, and also the reverse of that.
So you're going through the mock exam, presumably?
Yeah, like maybe the first 4 or 5 mock exams. I mean, we haven't gotten into how to order them, but I think with the simple ones at the very beginning, we would probably be okay if there's only one operator, or if there's only one connective.
Yeah, okay, that's fine. Yeah, okay, no problem. So, I mean, this, just to be clear about this, is a genuine university-level course. I've taught at a university before, so this is like the level of... It's really easy to begin with. In fact, the whole course is actually really easy. There's a lot of content in there, but there's nothing that's actually difficult. But this is a university-level stuff that we just get in for free. So, I mean, yeah, by all means, I'm absolutely happy to share it. I think everyone should have.
Should everybody send you a bottle of wine? Is that what you're asking?
That's it, exactly.
Was it you want Pliny the Elder, don't you? That's what you really want.
I would. I'd really like one of those.
Get Alex some Pliny the Elder.
See, I need to live in California.
Whatever the heck you just said, I'll get it for him.
Yeah,
You've got to be in California.
I need to be in California because I can't get that. I can get Founders stuff here. I can get,
I can
Kentucky
get
Breakfast Stout and other great things like that, but I can't get Pliny unless I go way out west. Which
Well,
I
if it's
will
from
be
France,
doing.
I can get it for you. I can't get it any other place, but...
Yeah. I will be hitting out west. We finally, my fiance has settled on a honeymoon location. We're going to Napa Valley, so you're going to get some good wine.
Oh, congratulations.
One of my most favorite spots on the planet.
It is nice.
Nice.
We're trying to figure out what we're going to do. Like, we're going to do more than just go to Napa. Like, let's stay there for 10 days. Okay, I think there's more. We'd like maybe go to San Francisco or
Death Valley.
area.
There's a lot of places you can get to from there for sure.
Yosemite Park. That's good to go to. Climb up the falls and up.
Yosemite?
Dome.
I didn't even know what you were saying for a second there.
Joke to one side.
Yosemite.
Yosemite Park.
Yosemite.
I would pay actual money if someone would send me a bottle of Pliny the Elder. I'm not joking about that.
Okay, say it again. Write it in the slide chat. I'm doing it, man. It's yours. So you got to write it because I have no idea what the hell you're saying.
Pliny the Elder.
It's a double IPA, isn't it?
No.
It's
P-L-I-N-Y.
An Imperial IPA, I think. There's two. There's Pliny the Elder and Pliny the Younger. One of them is an
there's
Imperial
two of them.
IPA.
Yeah.
I thought they were both double IPAs, but one was just
got
rarer
burnt
than
in
the other.
Vesuvius and the other one didn't.
Alex, there's one condition. We have to see you drink it.
Fine, happily.
As long as we don't let Dragnot open it up, we'll be fine.
It has to be a six-pack
That's
as
an
well.
inside joke. Me and Fabio had to walk him through using a wine bottle opener on Hangout. Oh, it was embarrassing.
Yeah, there's the beer advocate bit on it. It's apparently pretty wonderful. Although, do you get Hop Slam ale in California? Because I got some of that downstairs.
We have a lot
Bell's
of
Hop
great
Slam?
breweries here, like tons.
Yeah, I don't think Bell's Hop Slam makes it out to California. At least I hope not. So I can go, haha, I have some, and it'll be awesome. But if it doesn't, then I'm like, haha, oh, you shit, you have it too.
Every philosophical discussion turns into talk about drinking.
Captain Awesome, of course, is
Funny
in.
enough.
Is Captain Awesome in Los Angeles or San Francisco?
Or like Nietzsche, madness. Woo.
Well, I think I should drop the link to the Philosopher's Song in here while we're at it, if you're going to talk about beer.
Right, I really do have to go though, so but yeah, so we'll do this again, hopefully next week the same time.
Brilliant.
All right. Thanks,
Okay.
Alex.
So thank you
Take
so
care.
much, Alex. I can't
No trouble.
express enough how much we appreciate it.
Fantastic.
Thanks,
Yeah.
Alex.
Absolutely
It's just
fine.
incredible. And then if you guys want to stick around after Alex leaves, we'll play around a little bit with this.
Yeah.
Then if we have to wait a whole week, well, all right.
Oh, I'm
I can handle
excited.
that.
Oh, I can't wait already.
Me neither.
All right, see you later, guys.
Thanks.
Thanks, Alex.
See you, Alex.
Bye, Alex. I have to go too. Lunchtime. Goodbye, all.
Oh,
Thank
you were
Alex.
going to be our teacher, but okay. We'll see you later.
Get the SWAT out of class.
I didn't know that was part of the deal.
That's actually
I have to go.
Ozzy's been in teacher mode for a few days straight now with some excellent stuff.
Oh, the thing yesterday was
earlier.
fantastic. Ozzy, that was
Talked
great
with,
yesterday.
Gary and Alex earlier on fallacies.
Yeah, that was an awesome show.
That was brilliant.
Yeah,
Your
well,
content has been quite informative lately, so thank you.
I feel sorry for Alex because he went from you and Gary to Xbox and Trey.
He barely lasted 10 minutes. It was,
No, he didn't
I think
last
his
long.
content was less than 5.
I was pulling my hair out.
I have tea. I must leave. Thank you. Click.
Click.
So,
It was really great though. His content was spot on. He says, "Well, yeah, let me explain it like this." He's like, like with math, when you put it out in real numbers, 1, 1.5, there's 1.25, and he's like, it's an infinite either way. But he's like, perfect analogy. And Trey's like, no, it's not. Bad analogy. Shut up.
Oh God, dude, I missed it. I haven't watched this yet. I'm really looking forward to that.
It's
Oh,
literally,
God.
it's the whole thing's very long, but his content is at the beginning. It's only about 5 minutes.
Yeah,
It's all we really
I
need to
don't
say.
think he made 10. He was
Yeah.
in there. Trey went on some salad binge, and Alex, you could see.
Alex was about to be pwned. He was about to be pwned, and he fled in terror.
he was.
Yeah,
he walked
that's
his
it.
dog, so we need to watch out,
Yeah.
right?
I
Yeah.
When Alex
realized-
needs tea, it's the same as somebody else needing to
That's-
walk his dog.
That's Trey.
I think it was his way of thinking that either I'm going to have to repeat myself or be a dick to this guy because there's no other options here. I'm just going to leave.
Well, JD, if you've watched it all, I got him later on. I abused Trey Jadlow in the last half an hour or last
You
20
did.
minutes.
You were awful. You were
So
so
you
mean.
have to. There's no other choice. He's so obnoxious. You either have to just keep your cool forever and just repeat yourself forever, even though nothing's getting through, or just be like, you dumb motherfucker, will you just stop being this idiotic? You're driving me nuts.
He's just so self-confident and smug. It's just I'm not, and he guffaws at bloody everything. It's just.
But I don't. I could be wrong about everything. I don't know anything. I'm just a dentist.
Well,
Yeah.
wait. Does
But I've never
anything
been defeated
happen?
in my argument.
Anything happen? Does it? Does it happen? It does happen. It changes.
It changes.
It happens. It's got to be self-existent.
Pure being doesn't change.
Okay, well, maybe we should go back to the whole point of the thing, or we can go about this.
All right, so I want
Talking
to
shit Tuesday
quick,
light all of a sudden. Let's.
let's do this before we practice. If you guys want to practice, but before that, I would like to hear from Rumpus because I read a thing that physics, some physicist.
Somebody needs to.
Can I just say physicists are the sexiest creatures?
Yeah.
But anyway.
Helena, you have to
Physicists
represent
an actual
the.
infinity, a real live actual infinity.
But I posted it too, didn't I? Did you not see my post to you
Yeah,
about
I
it?
saw that
I
last night.
didn't see the post, but I remember reading an article about that.
No, I posted it to you. I got it sorted out for you and posted it to you yesterday.
Did you really?
I did.
Oh.
It's my pleasure.
Well, why don't you tell us a little bit about that? Because this is an incredible thing. I mean, this defeats premise 2 of the Kalam without the need for so much philosophy, right? I mean, it's like uncaused things. Can you tell us a little bit about how they did that? How they did that with light? What the hell it was?
I can't really because I only read half of it because I was doing something else. I was busy trying to get prepared for this, and I therefore didn't have time. So I've only read half of it. But they definitely claim they've emulated the Hilbert's Hotel in a quantum level in some with light. I can't remember now with light or electrons. Damn it!
It was light. They said they did it with
right.
light.
Okay,
and to me, what this means, I mean, this is what I think it said, is that they have created an actual infinity.
That's right. And the thing about William Lane Craig is, of course, he claims that you can't have an actual infinity. I can't remember why it invalidates his position, but it apparently does, and so he's always disputed this hotly, and he had a big fight with Sean Carroll, I think, about the existence of these things, and yes, indeed, it does seem as though we've got a physical infinity. Though Dinah Cats Love Me put a comment on my post to you, saying that it's not quite the infinity that he thinks it is. So Dinah Cats Love Me is disputing it's quite the same, but anyway, the article by this physicist claim it is exactly like Hilbert's Hotel, so I'm going to go with them for the moment. But yes, I haven't read up on it, unfortunately, for you, Helen. I'll give it a read, and next time we have a hangout, I'll perhaps try and I'll investigate it and see if I can explain it.
That would be great. That would be really great. I would love that.
I'll repost it to her right now. I'm on your site. I'll just fire it back.
Thanks, James. Yeah, yes, right. Yes, that's right. You saw it, didn't you? I think.
Yeah, I posted. I replied to it.
Yeah, you did. That's right. Yeah. Yes, I did.
See, my question to you was, no matter how you define infinity, you can always add one more, and it's never.
Oh, that was it. Yeah.
See, that's kind of the problem with, like, I don't think it was ever meant to be an integer. I think it was always meant to remain a concept like zero. Like, there really isn't anything zero. It's just we didn't know what to do between 1 and -1, and they invented the zero thing. To me, it's always been just a concept.
Wasn't it? Who was it invented zero? Was it
Indians? There was a guy in India at about the 10th century, I think.
It was in Muslim world, right? I mean, back when they were kind of.
No, I don't think it was Muslim. It was Hindu. No, it was Hindu.
Hindu, I believe,
Hindu.
yeah.
Okay. Interesting.
Yeah, and then the Arabs picked it up because they obviously found it useful, and then I think in France, or Italy and France then picked it up, and then it got to Britain. In about the 12th century, and we didn't like it. We hated it because all these people, and of course the money changers, they were all used to doing stuff with Roman numerals, of course, which is next to impossible to multiply two numbers together using Roman numerals. So that was a very well paid thing to do, and of course this idea of zero that was anti-Aristotelian. Aristotelian, yes, but it's going to have a go at me about that, getting that right again. Aristotelian, yes. And so there was a reluctance on 2 points. The money changers didn't like it, and the idea of zero, of nothing existence, was anti-Aristotelian. And so it took about 100 years or something to really get used, and then kick out all the Roman stuff.
Yeah. I'm looking at Hitchens, because I remember him mentioned that in his book. Apparently the Mayans also came up with the concept of zero.
The Mayans?
Yeah.
Oh, really? Okay, I didn't know that.
Okay, so one particular side of the Mayans had also managed to come up with that beautiful concept of zero to which I alluded earlier, and without which mathematical computation is very difficult. It may be significant that the papacy of the Middle Ages always resisted the idea of zero as alien and heretical, perhaps because of its supposedly Arab, in fact, Sanskrit origin, but perhaps also because it contained a frightening possibility. I like that last.
And of course, if you think about zero, you can't have zero because you can think about it and model it in your head.
That's right.
You don't get the Trey Jadlow reference. Yeah, Trey Jadlow, remember, he doesn't exactly believe the concept of nothing. If you think about it, it ceases to be nothing. What's the difference between zero and nothing? I'm wondering if Trey Jadlow can think about zero.
It's kind of fascinating that something so integral to modern mathematics is relatively new. You think they would have been come up with 2,500 years ago, like very, very early on, but no, we didn't have the concept yet.
Well, Well, I suppose the Greeks did. Yeah, I mean the Greeks didn't have. Yes, I mean the Greeks didn't have zero. I mean they dealt with just mostly geometry. Yeah, they didn't have proper mathematics. They couldn't understand infinity either, or irrational numbers. I mean, this is when Trey Jadlow goes on about his bloody Aristotelian bollocks. There's all these. The whole wad of concepts that the Greeks didn't get to grips with, led them to believe obviously things that fell heavier things fell more quickly than lighter things, and the light came out of your eyes so that you could see. He couldn't handle zero either. They couldn't handle irrational numbers. They couldn't understand pi, and they had the four elements, of course, something they believed out off the top of their head. I mean, there's so much bollocks coming out there, and Trey embraces it as though it's God's truth.
Well, it's pretty amazing that he has to keep his some of his philosophy in 2,500-year-old writings. Yeah, I mean, exactly. Like really, we haven't. It's like holding on to, like I've been arguing with somebody about spontaneous generation, which Pasteur basically put to rest in the 1850s, but he's holding on to it as a cornerstone of evolution and abiogenesis. And I'm going, we've answered this question a long time ago.
All right, so who's up for a quick practice? You guys up for it?
Well, sure. The fun one was one of the last two, the conditional.
Which, go on.
Excuse me. Well, it took me a minute, but then I realized, okay, we're talking about just the truth of A, then B, not anything else.
Right.
Because like you said, we normally think of it reverse as affirming the consequent would be bad, but like, well, hold on, we're not actually doing that. The first is starting to the other end.
Right.
And once I figured that out and wrote down like, oh, okay, makes perfect sense now.
Yeah. Right. All right. So let's do a quick one. Let me see. I'm going to find it real quick. Hold on.
Don't feel bad, Rumpus. I send Helena stuff a lot, and she doesn't either read it or reply to it.
Yeah, well, she's got so many admirers, of
She's
course.
just so busy. I mean, I can understand that.
Well, let me go ahead and put the thing in, like I put on the side chat about, it's a common one if it's raining and it's wet. It's actually used as an example of affirming the consequent, but in this case, we're talking about, is it true that if it rains, then it's wet? Yes, that is true. If it was true that if it rains, then it's not wet, well then it's not true that when it rains, then it's wet. But when you start replacing other ones, it's still true that when it rains, it's wet.
Yes.
So we start with both true. It rains is wet, obviously. That's also true. True. If it's not raining and it's not wet, it is still true that when it does rain, it is wet.
Right.
And if it's not raining but it's wet, it's still true that when it's raining, it's wet. But then there's the one that's false. If it's raining, it's not wet, well, that doesn't follow.
That's right.
So yeah, once I spelled it out in my head, I'm like, got it. All right.
Yeah.
No, but you got it. You got it. Let's start with an easy one, okay? So let's just practice a little bit, just real quick. Going back and forth between the natural language, and we're just going to do ones that just have one operator, or the proper word, I suppose, is connected, right? So
operator actually is well, certainly in computing, that's what you call an operator rather than a connective. A connective can include other things besides they might call it logical connectives, but I think it's better to call it an operator.
Well, in Merca, we only know them as operators, but
for
our purposes, they're connectives.
What makes you think that you're going to get away with that, Helen?
Get away with what?
Using the American only word.
I'm not. Did you hear me? I said connective.
Okay.
All right. Okay, so look. So here we go. So let's.
Fire, that's all.
So we've got let's go first from the symbols to regular language. Okay. So we've got P. So first, open parentheses. P.
You should going to present this.
No.
We can't. We've got to write it down, have we?
Well, I might be able to present it. I don't know. Let's see if I can figure that much out.
Okay, I shared that thing from Rump to you.
Yeah, I'll get to that sometime.
I know, I'm just saying, but you've got it again, so.
I think I am presenting now.
Yep.
All right, now somebody who has mods, click, to make it, so that it doesn't matter if it's talking.
And Helena booted from the Hangout.
All right, can everyone see it now?
Yep.
And can you see it no matter who's talking?
It's presented to everyone, yeah.
No.
Or well, it was. Nope, you ruined it. Damn it. Rump, it's all your fault.
Click, broadcast everyone or whatever.
That's what I've got. I've got you. I'm broadcasting, so I see it.
All right, so we just want to translate this thing here, right? Parentheses P up caret Q close parentheses, where P means Samantha will win, and Q means James is ill, and R.
What is the link between the A and the thing, the A in brackets and the P and Q thing in brackets? What's the operator between the two of them? What's the bracket?
So the A means here's the first one.
Oh, I see. Yeah. Oh, God, right.
All right. So
now I'm lost again. Thanks a lot.
To me, right? So this up caret means and. So this looks pretty easy, right? To me, it's Samantha will win and James is ill.
Yes.
Does anybody disagree?
Nope. That's it. It's easy.
Samantha will win and James is ill. There's our answer. So we got that one. So next. Next is, if I can get this mouse to work. Okay, so B, and that B just means here's number 2. So this little symbol is the not, then parentheses, P, down caret, Q, close parentheses. So this little down caret, everyone remember, that means
or,
and this one means not, right? So we actually have 2 little operators. I told them I wouldn't go past that, but let's just push it a little. So who wants to try to translate this one?
Well, that's obviously Samantha, it's the not of Samantha will win or James is ill. So So it's not the case that Samantha will win or James is ill.
Yep.
But it is the
So-
case that Sam will win and James is ill.
I don't know.
So
I don't know about
James, so Samantha will. So James is sick.
You
I was adding in the first one to the second one.
what was it? What was that?
So to me, the parentheses is and you know this is why he told us not to go this far.
What's your problem, Helena?
No, I have no problem.
Okay, what?
Yeah, I
Because
mean,
you-
I didn't mess anything up by that, did I?
I don't think so. To me,
Or is
the
that, you know,
parentheses
I just remember the first
means-
one, so
The parentheses means to me that this negation is functioning is distributed right among both of these, right? So it's
Well, no.
not the case that this whole thing.
yeah, it means PRQ is false. That yeah.
Yeah. Okay.
No.
Rumpus, no?
It means no. It means that it's the not of the or operation between P and Q.
Right. I think we're
Okay,
saying
so that's different from what I said.
It's not the same as not P or not Q.
That's right.
Yep.
It's
No, that's
not
not
or.
That's not what I meant.
Okay, all right.
It's not or, right? It's not or. It's is, or it's and. So they're
No, it's
both
an or.
sick. So one, Samantha's sick and James is ill.
You're right. So I agree with Rumpus, right? It's not the case that Samantha will win or James is ill.
And you can
That
invert
actually,
it.
I was gonna say that follows from A too, right? If we combine them.
Oh, I wish.
Well, we're not combining. We'll get in a lot of trouble for doing that.
Well, it's like if A is if P and Q, then it can't be P or Q.
Why can't you present properly, Helena, so we can see all
What
the
am
time?
I doing wrong? Okay, let me go back to the Hangout. Hold on.
Was I wrong? I thought I had it.
Hangout. And now I go to present to everyone.
Yes.
Rumpus, why don't you click on Helena?
Hey, now it worked.
All
right.
Now it's presenting to everyone.
If you get a white box, I think you'll find you won't lose her.
So is that okay now? Somebody else talk.
No. Oh, I see. Oh, right.
Good?
Yeah, it's working great.
All right. So,
Yeah,
and
what's
pardon my
the-
fan, I'm getting a new
what's the
computer
journal?
because I tried some.
Oh, see, we can actually decide who we can present ourselves
Absolutely, yep.
Oh,
Yeah.
right.
Yeah,
Okay.
if you have mods, you can do, your God.
Well,
Right, so we
even
all
in a
agree that
regular
this
hangout-
is-
No, we're not mods. We're not mods.
Even
Well,
in
you
a-
aren't.
in a
And
regular
you call yourself an atheist.
in a regular hangout, if you only want one icon up, then you just click on them. You get them white boxed, and you'll only
Yeah.
see that person, no
So you
matter
can
who's
select your own
talking.
output, yeah.
Absolutely.
All right, so here we go. It is not the case that Samantha will win or James is ill. We
Oh,
agree.
so I got, yes, which is exactly
Yes.
what I said, yeah.
Perfect. Yeah, and
Hold on,
that's
you
what
knew
you
these
said.
answers ahead of time, so Helena, you knew.
I didn't know shit. If you notice, I suggested distributing the knot, right?
You did, you naughty person, yes. which is bad,
Just
yes.
terrible. All right, so next. Okay, we're getting a little. This
Holy
is probably the last one we can do, right? But to me, so here's how I'm doing this so far: is I'm reading this, I'm saying imply.
That's
Then
right.
after I run the sentence with imply, then I put the if then in because I'm just a beginner, right? So the C, remember, it means this is the third one.
Yeah.
All right, who wants to try this one?
Well, okay, I'll give it a go. It
Okay.
means that if Q and R are true, then not P is true. Or you could so we go. So I could say it's Q. So James is ill, and so if James is ill and Tim is better than Zach, then Samantha will not win.
That's
I
right.
agree with that 100%. I totally agree with that. The way I would have done this, right, as a beginner, I would have gone, So I would have gone, James is ill and Tim is better than Zach implies that Samantha will not win. And then I would have gone from there to, well, if it implies that, it means if this one, then this one. So I would have had to take the 2 steps there. Does anyone else disagree?
No, it sounds good.
Let's see what he says. So he says, if James is ill and
Then not P. Exactly.
James is
Trump
better than Zach, then Samantha will not win. Okay, cool. All right, so I think that's as
Rumpus
far as
for
we
the
can go
point.
without getting in trouble here.
I said rumpus for the point.
Rumpus for the point. All right, I'm going to close this because actually, to go from the A-B, the sort of general case that we've been learning, over to putting the Q's and R's in, right, and talking about specific propositions, there's a way to do this where you number the operators and things like that. That makes it so that it's kind of foolproof, and we didn't get into that, so we're going to have to stop here and wait until a whole nother week. But I guess that's okay.
Oh, I'm looking forward to it already. Oh, Alex was brilliant, wasn't he?
He's fabulous. I really am going to buy him a case of whatever the heck he was saying.
Pliny the Elder.
Pliny the Elder.
But Pliny the Elder, like the historian from the 1st century.
That's right. That's right.
Yeah, so
unfortunately, the problem with it, you see, it's made in a very local brewery, and it's not in the shops, so you can only buy it in California, and they've got the restricted outlets, so you can't just buy it anywhere. And I don't think you can even order it online. You have to, I think, almost physically go to.
Well, JD's going there.
Yeah, exactly. So that's why JD's obviously in the ideal one, or someone in the area like Captain Alsomo or something, or.
I think Deidre's in San Diego.
Deidre is in California. I think Jade is out that way. I think she's in Northern California. I think she's actually
Jade,
in.
Of course. Yeah.
I think she's actually in San Francisco. So
we have to get somebody to physically buy it, and then ship it physically, right?
Yeah.
So
I think Dreas is out there too.
Okay. So I'll be happy to pay the money. But if I can't do the actual physical stuff, somebody do the physical stuff, I'll pay you.
Yeah, but isn't Pliny seasonal? Like
I have no clue. I don't even know what it is. Is it?
No,
wine?
no,
What the hell?
it's just a pale ale. No, it's not seasonal. No.
Well,
But they
no,
have
it's an IPA. Pliny's an IPA.
Yeah, but that doesn't mean seasonal.
Well, the thing is, because it's so high on Beer Advocate's list, a lot of those tend to disappear quickly. They tend to be short runs. I don't know if that's true for Elder. I think it might be for Younger. One of the two. There's Plenty of the Elder and Plenty of the Younger. I think they're both
That's right.
double
You're right.
IPAs.
You know that. Yeah, that's right.
Well,
yeah,
the
Elder
harder
one
it is
the
to
tricky
get, the more he'll know we appreciate him.
Yeah.
So.
Because it's been voted, I think it was voted top beer in the world or something ridiculous. I mean, it's
We're close
won
to it, yeah, it's way up there.
5 years in a row or something. It won.
Yeah, Hop Slam is another Imperial IPA that's extremely sought after. It's Bell's Hop Slam, and they just came out with it. And of course, usually like last year, within 3 days, gone. There was it. It was supposed to be like for the whole month, 3 days, all it lasted before it was all gone.
I'm just amazed.
Elder might be the same way. I don't know if they have enough production yet.
Well, I'm going to take it off air. I'm going to take it off air real quick, everyone. And anybody who wants to come in, right? You can always come in. Just get in.
Viewership just skyrocketed like 300 people when you start talking about beer. It's like, woo, beer talk. I want to come in. I want to watch.